Here's a kinematics two-dimensional test for you. So this is kind of on the assumption you're a grade 11 and you're taking kinematics for the first time. This test isn't the easiest one. There are some easier questions, but there's also some tougher questions, which I hope will challenge you. So I'm going to put a link in the description below to this particular test. You can download it and then solve it and then come back and then look at the solutions as I go through them, or at least as I hope to go through them. So let's take a look. Now, one thing with regards to just rounding, okay, so, round your final answers. I'm going to just assume I'm going to be rounding to the same number of significant figures as the measurement which has the lowest number or the least number of significant figures in the measurement. And in the intermediate steps, I'll try to keep several decimals together, okay, before I start doing the rounding at the end. All right, so question number 1, so here it is. Break down each vector into its x and y components. So this is one of the easier questions, at least I hope so. So here we have velocity and we have a displacement, and we want to be able to break these things down. All right, so let's take a look at the first one. So the first one is, negative 3.5 meters per second, and notice it is north 10 degrees west. So this is, I guess on purpose, what I've done is I've made it negative because I wanted you to realize that the negative actually will switch the direction, right? So if you're taking a look at this, the direction of this, if you're going to be starting from north, you're going to be going 10 degrees and then you're going west. So this would have looked like this. That's kind of how it would look like. 10 degrees is going to be very close to the vertical. Now, because of the fact that it's negative, so this right here, it's going to take your vector right there and it's going to actually switch it around. So it's going to go in the opposite direction. Okay, so it actually looks like this. Okay, so this is how it would look like. So the 10 degrees that we have, so this 10 degrees right here is the same 10 degrees that you have over there, if you remember your actual angles. And this just comes from negative vectors, all right? Okay, so now we can start calculating this. Now, once you do this, then this becomes positive. So this is 3.5, meters per second, and it is now positive, but it's in the opposite direction of the actual direction that they gave us. So now if you want to break this down into its x and y components, so you can certainly do that, and I'm going to now break it down and make a triangle out of this. So this is my angle right there. Okay, so I'm going to make my right angle triangle here into pieces, and what we have is this is 3.5. Okay, and this would have been my x component, and this would have been my y component of that velocity right there. This is now 10 degrees, and I can go ahead and break this down. So the x component that you have is nothing else but simply the 3.5. Now notice the angle is, so x is actually opposite of the angle, so that means we're going to be using sine. So this is going to be sine of 10 degrees that we have. And the answer here is going to be positive because it is in the direction to the right. So at least this one is assuming positive is east. So if you do that, here's the calculator. I can just put it in here. So times, and this is going to be sine right there, 10 degrees equals. And so there you have it. So it's a rather small one. Okay, so it's said to round to the same number. So it's going to be 6.1 meters per second. Okay, and this would have been on the east side, or at least if it's the x component, that's what we would have. So that's the velocity. Now the y component that you would have, so well, the y component is related to the adjacent angle. So this is going to be 3.5, and then this is cos of actually 10 degrees that you would have. So this would have been 3.5 multiplied by cos of the 10 degrees. And this is obviously is going to be much bigger. So it's about 3.4, again, rounded to 2 sig figs, meters per second, okay, that you have. Now, the only thing is that this component right here, because it is going down, this is actually negative, right? So negative meaning that it is pointing down or south in this case, okay? So that's what you would have. So, or with respect to, north being positive, that's why, you would put a negative there. So here, if you wanted to do that, okay, this would have been in the actual direction, okay, that you would have. And now only if you wanted to know the x and the y components just with respect to an axis, then you can remove these, and that's what you would have as your answer, okay? But it is down, right? So hence the negative that I put in there. So now the next component, so the part B of the question that you would have, is going to be the 150, now this is kilometers, notice at 68 degrees to the horizontal. So 68 to the horizontal, if you would do that. So that's going to be in the first quadrant. It's going to be somewhere over here, okay, that you have. And I guess, we can assume. So here is your 68 degrees to the horizontal. So this one, breaking it down. So again, you can break it down and you can, put it into its x and y components. So x and y. So both of these now will be positive. This is 150. And this is 68 degrees. So the y component would have been 150 kilometers multiplied by, now this is going to be sine of the angle because y is now the opposite, so you can obtain what that is. And then your x component that you would have is going to be 150, and this is cos of 68 degrees. And again, you're going to get whatever that answer is. So plugging these back in here, so times, so this is going to be sine times 68, and that's 139. Well, this has actually two significant figures, so we'll round this to 140 kilometers. And then the other one, which is 150, multiplied by, this is now cos, 68 equals, and this is going to be 56. And that's going to be 56 kilometers right there. All right, so those are the two, and this would knock out question 1 for us on this particular test. So it would have been a little bit of work, but certainly something that you should be comfortable with in terms of breaking things down. And it will force you to remember, creating your right angle triangles and then correctly identifying the x and the y components. Here's the second question. Now this one would have taken us a little bit longer, so I've actually kind of pre-done this a little bit, because what it asks us is using graphing and scaling. So in here, if you were using graphing and scaling, that means you actually would have to graph something and then scale things accordingly, right? Because you would have been drawing it on a piece of paper if it was on a test. And you would need, indeed, a protractor of some kind, and then you would also need some kind of a ruler. So I'm going to assume, okay, so that on this ruler, okay, what I have, so this is 1, this would have been a half. But so from here to here, so 1, let's assume that this is 1 centimeter, right? So this would have been 2 centimeters, this would have been 3 centimeters, okay, and so on. So that's just a heads up for you. And of course, in here, we're starting from 0, okay, and then our degrees will tend towards this way all the way around 360 degrees. And I can use that, right? And I would need to use that if you were doing this on a test. Not all students are going to be doing this. I actually don't remember graphing and scaling when I was in high school, but I do think that it's important enough that you should, or at least your teachers should push you at least for 1 or 2 examples, because when you're in the real world and you start actually mapping things out and you start thinking about maps, you use scales quite a lot, and then you use directions, and you can use and find vectors that way as well. So here they're asking us for total displacement. Now the total displacement, I do draw your attention that it's a displacement of addition and a subtraction. So we're going to have to be careful here with the vectors. Here are the vectors, and these are position vectors that I would have, right? So it's telling us a position vector with respect to some particular reference. So how would you construct this? I'm going to just construct one of them for you, and then you would do the same for all of them. And then, I'm going to bring things together, and then we'll calculate it to see exactly, how would we do this. Because when you're doing and adding and subtracting vectors together, you know that you can indeed break them down into their x and y components. And that way, it is actually a little bit easier because it's purely algebraic. Here, it is graphing, so it forces you to understand, okay, how these vectors work, how do you align them, and then what the resultant vector is. In this case, the resultant is the total displacement, that delta d, okay, that we would have. So let's take a look. So I'm going to take a look at the first vector, right? And let's break this down. How would I actually construct this all together? So what I would have to do is I would have to create, okay, some kind of a vector, okay, in here. And now I'm going to take my protractor right here. So this is my protractor right there. And what I would have with this is I have to create some kind of a scale, right? So notice this is all in kilometers. So clearly I can't put kilometers on a page, so I do have to scale. Now, because of the fact that I had my ruler right here, and I said that, I have a centimeter, I'm going to create a scale where 1 centimeter is equivalent to 1 kilometer on a scale. So when I'm mapping it out, that's what it will be. It will be a ratio between centimeters and kilometers. So every single vector that I draw, the number of centimeters that it is, it's actually in kilometers. So that's number 1. Now this one is 3.5 kilometers. And what I would do is the following. So I would take on, now notice it says east, so you're starting from east, okay, and then you're going north, okay, as you're heading along. So I'm assuming, east is at 0 degrees, north is at 90 degrees, and etc., etc. So in here, if I would draw this, if it's 45 degrees to the north from the east, so what this would look like, it would look something like this, right? So here, notice the angle, 0, 10, 20, 30, 40. So it's 45, right? So this would have been something like this. Now, I have to complete this. So this gives me the actual correct angle of the vector, right? But now I have to make it 3.5 kilometers. Or, as I put in the scale, it would have been 3.5 centimeters. So now I need my ruler. So here is my actual ruler, okay, in here. And now I'm going to take this ruler, okay, over here. And I'm going to... Whoops, that's not what I wanted to do. Okay, let's go back to the ruler. Okay, and then I wanted to be able to rotate this ruler. All right, now why am I rotating it? Because I want it aligned, notice, with the vector. So it's exactly the same. And now I can measure, how long this vector is. And I want it to be 3.5 centimeters. So if you look at this currently, so if I'm starting from here, this is 1 centimeter, this is 2 centimeters, this is approximately 3 centimeters right there. And I wanted this vector, okay, to be 3.5. So I'm going to extend this to 1/2, and it still has to be at 45 degrees, right, to draw this correctly. So there you have it. So now it's 3.5 centimeters, or 3.5 kilometers, and it's at 45 degrees, right, north of east. So now I don't need the ruler anymore, so I'm going to take this ruler out of here. Okay, I'm going to shift this out, okay, just to remove it out of the place. And now I've created my vector. So now here is my vector, okay, that I have. And I would set this aside, okay, so this is my vector, or if you drew it, it would be drawn there. Then you can take a different color or something of that nature. And then you can start drawing the other vectors. So now I would have gone along and said, okay, let's find this one. And as you can see there, it's 1.75 kilometers, or it would have been 1.75 centimeters. Now it's, notice, starting from west, it's 20 degrees north. So that would mean, so well, here is west, right? And I got to go 20 degrees. So 20 degrees would have been over here. So it's going to look something like this. And then I have to scale it correctly to 1.75. And then I would do the same to this one, right? So I would scale this one together, okay? And then I would proceed. So if I would do that, okay, all these vectors, these are actually these vectors in here. So notice this was the first vector right there. So this is exactly kind of the vector that I had there. Okay, so that was the first one. This one is my second vector. So that's D2, right? And then this one is my D3 vector. However, D3, notice, because it's south, okay, it's 50 degrees east. So it would have been, here's this, and then 1, 2, 3, 4, 5. Okay, so it would have been going something in this direction. Now you might ask, well, why is it in the opposite direction? The reason for that is because I am subtracting here. So really what I'm doing is I'm doing this. Position 1, right, plus position 2, minus, which is really plus, of the inverse of the vector. So it's the negative of the vector that we have. And that would mean that's why it has been flipped. So this vector that I drew here is actually the correct vector. So it is the vector, okay, that is really, as you see there, okay, the vector that is coming from this. This is actually 2 kilometers, 50 degrees east. But what I've done is I've taken this, okay, and then now I have just made a negative out of it because I'll be subtracting. So now what do I do with all of these vectors? Well, I line them up, as you can see here. So I line them up. So this is the tail, right? This is the head of the vector. Then I take my second vector and line up the tail and then put a head, okay? And then I do the same thing. So now once I have those three vectors, the resultant vector, which is from here all the way to the end, so this vector right there, is actually the resultant vector. So this is the displacement done by graphing them and then scaling them correctly. So if I want to find out, so now what I would do is, now I don't really need this anymore. Let me kind of shift this out of the way here. But what I would do, let me remove this. So I would take this right here, okay, and now I would need that vector, and I can now measure it out, okay, entirely. So for instance, if I want to know what the magnitude, what the length of this vector is, I got to now take my ruler, okay, and I got to line it up in here. So I'm going to line it up. Okay, so from this vector right there, so here it is, as I'm going through, okay, and notice that, so this vector, as I'm aligning it, okay, so there you go, so how long is this vector? Okay, so now I can find that out. So I can count this up now, so, okay, so this vector is 1, 2, 3, 4, and then notice 1, 2, 3, it's a little bit over there, so it's, okay, so approximately 4 point, now you're obviously going to be guessing, so it's going to be about, a little bit over 3, so maybe, 3, I don't know, 1 or 2 there, okay, and this would have been kilometers because it's in centimeters. So now you have the magnitude, and now if you wanted to know what the angle is, so now you got to bring this guy in here, and from here, you can take this vector right there, so now I'm lucky enough with this particular software, and then I can take it and group it right there, right, so here it is, and notice, okay, it falls. Okay, so as you can see there, so 90 degrees, and it falls 10 degrees, okay? So here my actual direction would have been, so starting from the north side, which is the 90, and then I'm going 10 degrees west. And that is my vector, so here it is. You have now found out, okay, what that vector would be. So here is the magnitude, here's the direction, okay, and that is my overall result. So that's how you would approach these graphing and scaling ones. And indeed, you need a protractor, you need some kind of a ruler. If you have those, you can certainly do something like this and start drawing things out, okay, for yourself. So now, okay, as I kind of keep chugging along here, if I take this, and here is question number 3, it's the same question, but here the question says confirm your answer. Okay, so this is for our previous one. So our answer is now, of course, this will depend on how good your scaling is, right? And then your ruler. So we're going to be off probably, but in any case, so this was kind of what our answer was. And this was north 10 degrees west. So, give or take, we should be extremely close within that. So if I take this, I want to break it down into its X and Y components. And then those particular components, I want to break them down and then do the actual additions. Okay, so let's do that. So now we should know how to break these down. So this is going to be for my first component, okay, that I have. So let me, bring these in here. Okay, so I'm going to take this and bring it down here. So that was my first vector, okay, that I had. So now for this vector, okay, so as you can see there, so we're going to have an X and a Y component. So it's going to be something here and there. We know what this is. This is 3.5 kilometers, right? We know what the angle is. So this is 45 degrees. Okay, this is my X component. This is my Y component. So let's, break it down. This is all in kilometers, by the way. So let's see it, okay? So my breakdown, my Y component is going to be 3.5. This is sine of 45 degrees. My X component is going to be also 3.5. Okay, and then sine of 45 degrees. Now, sine of 45 is 1 over square root of 2, if you still remember your unit circle. Okay, but if you don't, then that's fine, especially if you're just in first year physics. Okay, so you should probably recall that, but we can grab out our calculators and see exactly what these are. So I'm going to just leave this for the moment, but these are my components. So now I'm going to do the same, but I have to do the same with this. So let's, take this one, Okay, this is my second piece, so this would have been my second piece right there. And now I can start drawing this one out. All right, so this is my D2. Okay, so that's my position there. And notice, okay, so with this one, okay, so my y is going to be positive, my x not so much. It's going to be negative. So this is my x component, and then, you know, my y component I'll have, that's this one. And for this vector, it's 1.75. So this is 1.75. So this is going to be 1.75. Now notice the angle, it's 20 degrees. So that's this angle right there. So this is going to be sine 20 degrees. Now the answer is positive within here. Now for my x component, 1.75 multiplied by, now this is going to be cos, okay, of 20 degrees. But this is going to be negative now because of the fact that I am actually going onto the left, right? This is going to be the negative component there. So those are now my D2. And now, of course, I'm going to do the same thing for D3. So within here, so this is for D3, you know, so what do I have in here? So I'm going to just grab this out again. So this is my last component that I have. And this one, okay, that I have, noticed that I am taking the negative of it, right? I don't want to take the opposite side that I have in there, right? So because really that vector, okay, so the way that it looked like, it actually looks like this, right? Okay, and then what we're doing is we're subtracting it. So now instead, okay, of subtracting it, I'm going to flip it right here, and I'm going to take its components. So I'll know the x and y components in here for this one. So this is going to be my y component, so again positive. This one is the x component, which again looks like it's negative. So for my y component, that's y. Now the angle, okay, so notice it's 50 degrees, right? So now this is, so originally, okay, so the way that it looked like was this. So this was, you know, 50 degrees here, okay, from the south side. So that means, okay, as I go along here, so, you know, this, okay, this would have been the north side. So 50 degrees is over here. So that means that this angle right here is 40 degrees, right? Because they make up 90 degrees in total for that right angle. So if that's the case, then my y is going to be, now this was 2, I think. Yeah, this is 2 kilometers. So this is going to be 2 multiplied by, and this is going to be sine of 40, and then my x component right here, this is going to be 2, and then cos of 40. All right, so that's what we would have in there. So there you go. Those are the 2 pieces. So now what do I do with all of these pieces? Now, of course, I have to be able to add them up. So I'm going to be adding up all the x components. I'm going to be adding up all the y components, okay, that I have. The x component in here is actually negative, right, because it's to the left what I have. So when I do that, I'll have the x and the y, so that would be the total, okay, so maybe I'll break it down in here, okay, and this is the x, you know, total, and then this is going to be the y total, okay, that I have, and I'm going to take all these pieces. So I'll do that in fast forward fashion. I'll actually compute all of these. You can compute it on the side for yourself as well. And then I'll add them all together, and then we'll find out, okay, what we have. So I'll be back in just a moment. All right, so I'm back in here. Okay, so those are the actual computed values. So this is what we have in there. And by the way, I just noticed, so here I actually put sine. Okay, this of course has to be cos, okay, with regards to this angle. So now when you're adding all of these pieces up, so this is what we're going to get. So now if you wanted to be able to visualize this, you know, for yourself, so here's if it's your x and y component. So notice it's going to be a very small little component in the x. So this is how it would look like. Okay, so it's going to be negative, and then there's going to be a much bigger component in the y. So this one's going to be much bigger. Okay, so that's this piece and then this piece. And of course, if you were doing this, then, you know, the resultant now, okay, so what you would have, okay, if you wanted to be able to draw this out for yourself, actually, let me kind of go up on top here. So I'm going to take this, and we're going to find out all the details now. So if I bring this up to conclude this, and then this is what you would have. So you're going to have, you know, a piece, okay, this is your x component, and then you're going to have a very long piece, okay, right here, which is your y component, and the resultant, so the actual displacement, is going to be the combination of those two. So this is your y, my apologies, this is your y, and then this is your x right there. So if you want to find this, which is really just the hypotenuse, so the magnitude right here, so that's going to be nothing else but simply taking your x component, squaring it, your y component, squaring it, and of course that hypotenuse, so maybe I'll call it h, okay, for hypotenuse, that's going to be squared, which means we're going to have to take the square root, right? So this is nothing new. This will probably date you back way into elementary school in terms of finding Pythagorean theorem and using it in here for vectors. So if I do that, you know, what does this actually give me? Because this is going to be interesting. Since we're squaring it, you know, we can put it as positive, so that won't really make a difference because once you square it, the negative will be gone. So that is squared, and then plus, and this is 4.35898. I kept numerous amounts of decimal places, as you can see there. So I've kept about 5, 6 in there. So if I have that, this is my result, and now I have to take the square root of this. So if I take my answer and now take the square root of that, okay, so that's approximately, so if I take this, is going to be 4.4. And remember, this was in kilometers, right? Now, what did we get when we were drawing this out? This was, we got 4.32, all right? So this is what we got. So notice how close that is. So we were off by, and of course, because of the scaling, you know, you're bound to make some error within there, okay? You would have to be super accurate and zoom in. But this is really, really close to the algebraic technique that we've just used. Now, how do we get this angle, right? Well, that angle, okay, notice it's with respect to the north side, okay, in here. So we can certainly get, okay, the angle. So notice that, you know, here's the angle right here that we can get. And that is just opposite over adjacent. So this goes back. So this is using 10 inverse, opposite over adjacent. So this is going to be y over x, okay, that I have in there. And of course, we're going to be trying to find it with respect to the north side. So we want really this angle right here. Okay, we want to see if, you know, if it's going to be close to 10 degrees. So we're going to have to take 90 degrees minus that angle. So let's see what this gives us. So if I plug this in here, so I'm going to use 10 inverse. So it's going to be 4.35898 divided by, so going to be 0.701677. Now you might ask, why am I not putting in the negative? Because I just want the angle within the triangle. So the angles within triangles, you know, there are no negative numbers there for the sides. The sides are all positive. And what this will give me is just this angle right here. So notice it's 80.85. So this is this angle right here. So it's about 80, 0.855, etc. So that's this angle now minus the 90. So that's the, you know, notice it's 9.1 degrees. That's this angle right here. This is 9.1 degrees. Well, when we were measuring it with our protractor, we got 10. So we were, you know, super close. So that's what this would be. So our overall result, so from north, this would be 9.1 degrees going west. And there is your overall answer. So very close to the scaling. All right. Okay, so thumbs up to that example. I think it was a great one. Here is a word problem. So this is question number 4 on this test. This is definitely very, very hardy when I was making this question up. So this is the current world record in the long jump, and it's 8.95 meters, which is crazy. Crazy how far that is. So Mike Powell actually was the one who set this, and I remember this has happened in the very early 90s when this happened, and has stood ever since. So it's been, you know, way over 30 years, I believe. Okay, at least as of making this video. So if that is the case, okay, so this is the current world record, right? So that's the total, okay, jump. At takeoff, it has been estimated that the angle to the horizontal for the takeoff, okay, so Mike Powell had about 24 degrees. And we're supposed to neglect any resistance. Now, what does this remind you of? So I hope, well, it's kinematics in 2 dimensions, right? So if you're going to be taking off, now obviously, Mike Powell isn't necessarily a ball here, right? So let's, just kind of do some kind of a stick over here. And then, so this stick is taken off, right? So Mike Powell, okay, so he's going to take off right here, okay? And what it's telling us that this distance, okay, so the world record is 9.5 meters. So that would have been the displacement. And, okay, as Mike Powell took off, okay, he took off at an angle of 24 degrees. Now, we don't know what this velocity is. Now, we know it's at 24 degrees, but we don't know what it is. So, can we, find out all of this information? So notice that for part A, it says, what was the velocity on the takeoff? Okay, so let's, try that out. So we have all the information given there, so in the diagram, which I highly encourage you to draw. So for these are really just projectile motions, right? So we have all kinds of different things, okay, to be able to think about. So there are X and Y components, right? So if we're going to be neglecting any resistance, really the only thing in the Y component is gravity. So we know that gravity is going to be pulling, okay, this long jumper down. I'll put a negative there. So that's what we know there. We know that at the highest point, okay, right here, this is at the highest point. So this would have been your H maximum, which actually, what is the H maximum? So notice that they ask us that in part B. But that H maximum, the velocity, at least the vertical velocity, so here, so vertical velocity, so Vy would have been 0 here at this max, right? So we know that. We don't know really anything else, okay, within here aside from that. So now let's take a look what we can possibly find. Now, how do we know this? Well, for projectile, okay, so what I can think of is I know that the acceleration, so the average acceleration is equal to the change in velocity over the change in time. I know that this is negative 9.8 meters per second squared. So that would have been, so your final at the peak max is 0 minus whatever your initial one was. Now, what was the initial one? That would have been V, and that is actually now sine of the angle, which is sine of the angle, which is sine of 24, right? So that would have been the vertical initial velocity that we would have. So this is, the initial velocity in the vertical, y. Okay, so that's fine. Okay, so this is what we would have. Now this is our overall velocity, and well, I don't know what delta t is. Okay, fine. So I don't know that. Okay, so that's interesting. Okay, so within here, so I have this. Now, what else do I have in here, okay, that I can use, okay, to be able to find these things out? What's another, okay, because right now I have 2 unknowns. I don't know this, which is what I'm trying to find, and I don't know this, right? Okay, so these are the 2 things, okay, that I don't know. I do know, okay, what the horizontal distance is. So in the horizontal, so my displacement in the horizontal, which is equal to 8.95, it is equal to, and this would have been the velocity, horizontal velocity, right, multiplied by the time, right, that it took for the entire duration. Now, of course, this duration is going to be longer than the peak. However, okay, we know, okay, so that this happens, okay, at the midpoint, right? So from here to here, this happens at the midpoint. And then, from here to here, it's basically symmetrical. So this is delta t and this is delta t. If I label delta t, so that's that delta t. So that's two of those that I have. So I do know the following, that it's 8.95 times the v. Now this is going to be cos 24 degrees because it's horizontal, multiplied by the time for the entire duration, which is going to be twice the time, right, as reaching the maximum, because that happens at the halfway point. So this is going to be twice as long. Now, why, did I do that? Well, why I did that is because of the fact that I am after this v. So what I'm going to do now, so this is, a hard question for anyone who's kind of starting these things. However, I'm going to take this, okay, and I'm going to use, and I'm going to isolate, okay, for delta t. So my delta t is equal to, so notice this is going to be v sine 24 divided by, okay, 9.8. The two negatives will cancel, okay, so that negative and that negative will cancel. Now, once I have this, I can substitute it back into here. So I'm going to try to substitute it back into here. Now, why I'm doing that is because now when I substitute it, I will only have one unknown, which is the v, okay, which is exactly what I wanted. Okay, so let's try that out. So I'm going to add a page here, and let's try it. So we have 8.95 equals, so this is going to be v, right, cos 24 degrees multiplied by 2 times v sine of 24 divided by 9.8. Okay, so now it's going to be v squared. Okay, so within there, so we don't need the vector anymore as we're squaring this out. So we have now, so now taking this, right? Okay, now I'm going to isolate this. So this is going to be 8.95. Okay, and now I have to get rid of this, get rid of this, get rid of this, get rid of this. So I'm going to, so this is going to be divided by, and it's going to be divided by 2 cos 24 degrees times sine 24 degrees, and this is going to be multiplied by 9.8. And that's what we're going to have. And now we can take the square root of both sides to find out what the answer is. So 9.8 times 8.95 equals that answer divided by 2 times, now it's going to be cos 24 degrees times sine of 24 degrees. And so let me just double check here. Yep, I put 2, okay, equals. So that is 118, 025, etc. So v squared. So we need to take now, this is going to be the square root of this. So our answer, okay, taking the square root, it's the same thing as putting it to the power of 0.5. And that's going to be, so 10.8, 639, etc. Okay, so we started off with 8.95, which is, 3 degrees of sig figs. 24 degrees is 2 sig figs, so we'll just round this to 2. So it is about 11 meters per second. So that's pretty cool. All right. So that was on the takeoff, this is what we had. Okay, so it's pretty quick actually, okay, on that takeoff, what that velocity was. And if you want to make it a vector, so this you would have said at 24 degrees to the horizontal, and then it would have been a vector. Okay, if that's what you wanted to be able to find. If you just were after the magnitude, it would have been 11 meters per second. Okay, so that's a really good question. Now the other question was, what was the maximum height? Okay, so for the maximum height, okay, so now we certainly can, since we know the initial velocity there. Okay, so we can certainly find out now delta t. Okay, so for that, so notice that our delta t right here, so this is what it was. So I'm going to just copy it. And if I bring it down, okay, right here, so I can now substitute the delta t in here. So this is going to be, well, so it's 11. Well, or approximately 11, I guess, multiplied by, this is going to be sine 24, and this whole entire thing is divided by 9.8. So what does that mean? This means 0.45654 seconds. So, it's not too long, okay, that Mike Powell has been in the air, okay, so for that. So approximately that much. And now with this, so the maximum height that you would have, so how would you find that? Well, once you know the time, right, the actual height, you can use the formula. So this would have been the formula for the displacement, except this is displacement in the y. And this is with your initial, okay, velocity. Okay, this is all in the y, by the way. So this is, vi times delta t, plus 1/2, and then this would have been a delta t squared. Now this delta t, okay, that we have just found this, so I have that. The initial speed that I have, okay, so that initial speed, I have to be careful there. So that's going to be, the 11 meters per second times, now because it's in the y, it's going to be times sine of 24 degrees multiplied by the delta t, so times 0.456, etc. Now notice it's going to be now minus because of the gravity, and then again 0.456, etc. squared. So we can now substitute all of this in and find out what that answer would be. Okay, so let's do that. Okay, so we have, so approximately, so give or take, 11 times sine of 24. I mean, it's still pretty high up in the air there. 1.02, so approximately 1 meter. That was the height that you have. So it's just kind of 1 meter, although I think it was probably a little bit more. Okay, of course, we're neglecting resistance here, so it's not purely ideal, right? There's clearly resistance when you're running, taking off, and going up in the air there. But that's what it would be, and this is how you would actually kind of go about trying to solve this question. This is an awesome question. It's a really hard one, okay, for grade 11. It's kind of like a really challenge exam here question. Okay, so that's one more example. Here is another, okay, so it's almost our second last one in here. So what do we have? So we have a drone flying north is dropping off a package, okay? So they're flying north. The drone experiences turbulence in its propellant that drifts the drone at 1.2 meters per second. Okay, so let's start putting this in here. So we want to go north, all right? So let's assume that this is north. Now we have, okay, so that is 1.2 meters east. So that's kind of trying to take it off course there. So that's what we have there, right there. And so that would have been 1.2 meters per second. That's east. And then throughout the flight, there is also an additional wind, okay, that we have of 0. Now this is west-south, west-south. So this is kind of in this direction, right there. And this is 0.85 meters per second. This is west 45 south. If the drone needs to end up at the house located 1.2 kilometers in 10 minutes, then what must be its constant heading velocity to achieve this? Okay, well, so heading velocities, I'll put up a link up above there. So that is, okay, so what should you be actually moving along, right? We're going to get kind of shifted back and forth here based on those, okay, kind of turbulence and then also the wind. So this is interesting. We want to be heading kind of north, okay, but this is not exactly what is going to happen here. So we have to overcome, okay, these actual disturbances and winds. Now we want to take, so notice that it is located, so the displacement is 1.2 kilometers, that's north, and we want to take, 10 minutes. Well, 10 minutes, so the total time, 10 minutes times, let's say 60 seconds, that's about 600 seconds. And then I'm going to change this to meters because everything is in meters there. So I'm going to put this 1, 2, 0, 0 meters. So I've just changed everything to meters and seconds for consistency. So, what do we need? Well, this is actually what we need, right? This is ultimately what our result wants to be. So if you take a look at this, then that means your velocity, okay, is going to be ideally you want this drone to be heading north, and it's going to be 1200 divided by 600 seconds. So if you take a look at that, that's going to be 12 divided by, so that's 2 meters per second. That's what we want ideally. So this is what we want as a resultant. And now we have these disturbances kind of all over the place, okay, pushing us both to the right, to the left, and then backwards a bit. Okay, so now let's think about, so this is going to be this. This is what we want, all right? And now, so for this, so this is what I like to do here. Okay, so now let's take this guy right here. So this guy is going to be pushing. Now we want this to be at 2 meters per second north. That's the ultimate goal. And we are having, okay, so this is going to be getting pushed out here. Okay, so let's see this. This is going to be getting shifted it out. Okay, so that's in this direction, right? So that's that. Okay, so let's take this out right here. That's one of them. Then I have the other one, which is going to be kind of like this. That's this one right there. So this is going to be shifting it back here, kind of looking like this. And notice that now, okay, in order to get what we want, we kind of would have to, so it's going to be, this is what we would need, the drone. So the drone, this is kind of the heading. This is what the drone would have to be. And notice that as a result, okay, so if we would start, okay, so our result, so from here to here, would have given us, 2 meters per second. So what we want is this. We want X to be 0 meters per second. That's what we want. And we want our Y to be 2 meters per second north. That's what we want, okay, to happen. That's that red line. So maybe I'll change this to red over here. That's our goal right there. Okay, so now what we're going to do is, okay, so as we're kind of chugging along here, so if we take this, so now we got to break this down. So what components do we have? Okay, so in the X direction, okay, in the X direction, we know we have 1.2 meters per second, so that's east, so that's taking it off course. And we also have, so that's that second one, that's going to be the 0.85. Now, that's going to be negative, and notice it's at 45 degrees, so it's going to be 0.85 times cos, right there, 45 degrees. Okay, so I can find what that is, 0.85 multiplied by cos 45. So this is 0.601. So that's that. Okay, and now this one is negative. All right, so that's pushing it out. So as a result, so notice what you will have in the x direction. So you're going to have 1.2 minus 0.601. So you have, so this, when you add these together, this is pushing you 0.599. So in order to have 0, then we need our drone. Okay, notice, so our drone has to be negative 0.599, because then it would cancel off this, because when you add these two together, it's going to get you back to 0. So that's that direction. So that means this piece right here, okay, so that's your x piece, that's the 0.599, okay, really it is west, okay, that it's pushing you away. Now we need to find the y. So now in the y, so that's this one. Okay, so if I'm going to make this smaller, I'll shift this out right here. Okay, so now in the y, we need 2 in total. Well, currently, well, there's only one piece, right, in the y, right there. And that is in the y 0.85 sine of 45 degrees. Notice it's going to be negative right there. Okay, so we have that. So that's going to be, okay, negative, it's down 0.601. So this is going to be the same thing because it's sine and cos of 45 is the same. So that is pushing you back. And now you have to overcome this, okay, and you overall want 2. So our overall piece, then it's going to be, so our y component is going to be the 2 plus, because that's what we want, and then we want to overcome this. So we need an additional 0.601, because 2 plus this and this is going to bring you back to 2. All right, so that means this is going to be 2.601 meters per second, and that's this entire piece. That's from, you know, here straight up. Okay, so it's going to be an extra little piece added in here, and that is your heading velocity. So your heading velocity that you have, okay, is going to be that. All right, so that's the x component and then the y component. All right, now if you want to make this component, okay, just to be exactly, and you want to find out what angle that is, you can certainly do that, right? You can find the Pythagorean theorem now. Okay, so you can take the square of both of them, take the square root, that will give you the exact magnitude, and then you can use the tan inverse to be able to find out, okay, what the angle is, and then whatever angle you want to be heading at, and that's what the drone will have to do. So notice the drone isn't going just straight north. If it did, it would get shifted away. So it has to kind of take a heading velocity to overcome those two, wind and the actual disturbance from the propellant. All right, so that's another great example, and really would challenge you here to be able to understand these vectors. All right, here's the last one. So that's the last example that we have, and we'll finish off this test. So for this last example, let's get ourselves started. So what are the givens? So an object is shot out of a tower 250 meters above the ground. All right, so here's our tower. Okay, let's say that this is the window. Okay, so this is 250 meters above the ground. The object is shot out at a velocity of 35 meters at an angle 60 degrees. So it's kind of shot out something like this. So this is going to be, that's 60 degrees. This is 35 meters per second. How long will it take the object to reach the ground? Okay, so this is another not a nice one, okay? So it's going to go kind of like that, right? So how long is it going to reach the ground, which basically means how long will the displacement, right? So displacement, you want 250. Now, this is 250, so notice right here. So that would depends on how you're going to set your references. So just be careful in here because you're going to be working in the y component, okay, of this. So in the y component, so what you have, so the displacement, if you are going to be assuming, okay, that 0 here, this is 0 and this is 250 meters up above, okay, then the displacement itself is going to be, so 0 minus 250, so that would have been negative, okay, 250 in terms of that, because that's the final, would have been 0, and then the initial is 250 above it. If you say 250 is, you know, negative and so on, you know, just make sure that you reference it correctly. And you want this because you want to make sure that you're assigning, I'm going to assign gravity to be down in this way. So the acceleration is negative 9.8. So I'm assuming up is positive here. Okay, so that's what I have there. That's meters per second squared. This one is in meters. So I have that. I have my initial. So this is my initial velocity, which is going to be 35. This is sine of 60. So I have that. And now I want to know, okay, so how long did this take? Okay, so this is what I want to be able to find out. So that's not the nicest of examples. So we have this. The change, so the displacement itself is equal to the initial velocity. I'm going to drop the vectors there, times t plus 1/2 a delta t squared, right? And we're trying to find delta t. So now we have all of these. So this is negative 250 equals, this is going to be 35 times sine of 60 times, I'm just going to put t instead of delta t, just for convenience, and then minus is going to be 1/2 times 9.8. The negative is just coming from the acceleration, and again this is just t squared. So all of these in general, let's do this. So 35 times, you know, sine of 60. So this is approximately 30.31, you know, just kind of rounded there. This is t, negative 250. And then, well, this one is easier. So minus 4.9, you know, t squared. Well, so you're kind of stuck. You have a quadratic. You're going to have to solve for t. So you're going to have to date yourself back. Okay, you know, solving for a quadratic, you can use the quadratic formula. I'll put up a link up above there if you've forgotten it. So this really, you know, tests your skills here. This is definitely a nice test here. Okay, so let's rearrange this. So I'm going to put 4.9 t squared. I'm going to bring everything to the left-hand side. So 31 t, and this is going to be minus 250 equals to 0. All right, so this is for your quadratic. So that's your A. This is your B. You know, this is your C. All right, so in your quadratic formula, okay, so what you have is, so if you remember, so negative b, so plus minus square root, this is, let me just do the quadratic formula quickly for you, okay, and then we're going to, so this is b squared minus 4ac. I have to substitute all of these numbers in here, okay, and then get my answer. Okay, so I'll be right back. All right, so I'm back. Now there's going to be two answers because it gives you plus and minus. But notice if you take 30 minus the 37, whatever, you're going to get negative, and time can't be negative, so you take the positive answer. So if you take the positive, you're going to add these together, divide this, so you're going to get about 6.9 seconds. So that's how long it would take. And that would have been the setup of this example. All right, super long test, okay, but there was a lot of really good questions here, okay, that would test you on two-dimensional kinematics. If you understood all of these, you know, projectiles and everything else, okay, it's going to get you really ready for all the future items you're going to have to do. You're going to be comfortable with vectors and working with them. Okay, thanks for watching. See you in a future video. Happy studying.